Hello. So this is an introductory tutorial on testing for the SARS-CoV-2 virus from an engineering perspective. To emphasize, it's just an introductory tutorial, and what it's doing is looking at the similarity between the mathematics that we use in binary classification in engineering and saying, hey, it's very similar to what you're doing with SARS-CoV-2 virus testing. This is really at first year undergraduate level and using no more maths than you would get in first or second year of A level. So why engineering? The answer is that in applications like sensor networks or radar or sonar or data fusion that I've worked in, we have different problems and different nomenclature than in COVID-19 testing. But a lot of the maths is similar. For example, statisticians talk about type 1 error. Epidemiologists might talk about a false positive. And in sensor networks, we might talk about false alarm. They all mean exactly the same thing. And it was this realization that we share very similar mathematics, conditional probability, Bayes' law, hypothesis testing, etc., that led me to say, well, can we look at the maths used in virus testing and approach that from an engineering perspective? I have to say again, very basic introductory tutorial. So let's start by looking at what I will not do. I'm not going to do any real data science. I'm not going to do any epidemiology, classification, rules, estimation, detection, decision theory, although I have worked in that area before. And so if you're coming from a data science background and you're looking for some new research results, then this probably isn't the best place for you to be. It's an introduction for first year, really, science or engineering students about binary testing. So what I will do, I'll give a very basic background to the virus, what it is and how we test for it. I'll introduce non-symmetric probabilistic binary channels, which we use in wireless communications to help understand the test outcomes. And I'll look at trade-offs in the test parameters and introduce the idea of receiver operating curves and look at how the results might be improved and give examples throughout. So again, the tutorial is at first year engineering undergraduate level, and all you really need is Bayes' theorem and to understand what conditional probability is. In fact, if you were from school and first or second year of A level, you would have covered much of this in terms of the maths, so it's not difficult. But of course, you have to beware of dangerous fake science. It's all around us, and it makes outlandish and outrageous claims. And we have to sift out what is fake and what is a conspiracy and what is true science. So what follows now, I hope, will be true science. Okay, so this is section 1, introduction to the virus and testing. I could go straight into looking at binary classification, but I wouldn't then put in context why we're doing the testing, how we're doing the testing, and why it might have errors. So this is just a gentle introduction to the virus and why we need to test for it and how we can use those test results. And then in section 2, I'll start looking at the mathematics of binary classification. So this is a picture by Poussin, and it's the plague of Ashdod, which I believe is from the Bible, the book of Samuel. And it just reminds us that plagues and viruses have been around for thousands of years. And in this particular picture, you can see that certainly people are not socially distancing, physically distancing. So maybe we should redraw this in the current light of COVID-19. So what is a SARS-CoV-2 virus anyway? SARS-CoV-2 is part of the coronavirus family of viruses, and it's only emerged in the last 5 to 6 months. If you look at it, this picture is probably very familiar. It's an RNA genome in a protein shell. And if you look at that genome, it's only got about 30,000 letters in it, whereas the human genome has got billions. So although it seems relatively simple compared to human genome, it seems to be causing a lot of problems at the moment. It's a diameter of 100 nanometers, and compared to a human hair, That's 100,000 nanometers. It's 1,000th the size of human hair. And it's 1,000 times bigger than a hydrogen atom, approximately. In addition, there are 10 to the 31 different viral particles on Earth. That's obviously an estimate. And there are 10 to the 80 atoms in the observable universe. So quite big numbers and quite small numbers here. Okay, I first noticed the number of COVID-19 infections in the UK growing rapidly when I was watching the news one night, and I went to the government website and downloaded the data on the cumulative number of COVID-19 cases in the UK. That's the total number of people who've been infected since the virus began. And I noticed that it was exponentially increasing. Now, the press talked about exponential increase, but didn't explain what it was. It's that equation x of n equals x of 0 into 1 plus k to the power of n over 3, where n is an integer referring to the day. And if k is approximately equal to 1, then you'll have a doubling roughly every 3 days. If you continue that doubling into April, then what you get is at the end of April, 42 million people have been infected with the virus. Now, that's not going to happen for many reasons, but I simply wanted to illustrate that an exponential increase is indeed very serious, and I think it was that realization that changed perhaps or influenced government policy when they saw, or the mathematical modelers were predicting how this, without any intervention, could rise to really high numbers. So how do we model the spread of any disease, not just COVID-19? So what's often used is this nonlinear model called the SIR model. And the SIR model is three nonlinear differential equations, and there are three variables, S, I, and R. A fourth one, T, is the independent variable. So N is the number of people, say, in the country. S of T is the number at any time that are susceptible to the virus, so they don't have immunity. I of T is the total number who are infectious at any point in time. And R of T is the total number, the cumulative number who've been removed by death, or else they've recovered and have got immunity. And if you try to solve those equations, you can do that, those cross-coupled equations, by using Euler's method. And if you look down below, you get, that's such a classic plot that you might get. And if you look at the green line, this is telling you all the people, excluding death, who really have had the virus. And it's plateauing at about, 0.5 of the population, probably due to some sort of herd immunity. Okay, so what we're looking at here is we're looking at a paper in the bottom right-hand corner, which came out recently. And these Chinese authors, they looked at the original SARS data, and they predicted what might happen from the SIR model. And as you can see, the SIR model is very close to what actually happened. They also put in the actual COVID-19 actual infectious rate, which, as you can see, is increasing exponentially. And this reminds me of what George Box, the statistician, said, who was responsible for the famous Box-Jenkins method. All models are wrong, but some models are useful. You can see that the prediction model for 2003 SARS is wrong because it doesn't predict exactly what happened. But it's pretty close, and so it's pretty useful. If it predicted a sinusoidal variation of I of t in 20 years' time, it would be wrong, and it also wouldn't be useful. So this is an example here of a model that is wrong, like all models are, but that certainly is useful. So also be very careful when looking at data. If you look at the daily cases of COVID-19, or you look at the daily deaths, you might see a pseudo-periodicity with a period of 7 days and think you've discovered something interesting. But in fact, that's nothing more than the fact that there is less registering and reporting at weekends. Okay, so why is there a problem in the first place? So I want to look at 3 points here. The first one is, how fast does the virus spread? And that's given by the very famous reproduction number, which you've probably heard of every single day. Often misquoted as the reproduction rate. It's not a rate, It's a dimensionless constant, and it's equal to beta times tau. And R0 is the number of other people who will be infected by one individual, assuming no population immunity. Beta is actually the rate, the number of infections per unit time. And tau is the infectious period. So you multiply beta by tau, and you get the total number of people infected. And you can reduce those by social distancing, PPE, etc. Now, if you want to get to the famous herd immunity, then you need a fraction 1 minus 1 over R0 of the population who are going to be immune. And in that case, you need to use what's called the effective reproduction number, R sub E equals R sub 0 times K, where K is the number of people in the population who are susceptible. So if K equals 1, 100% of the population is susceptible. If K equals 0.7, it means 70% of the population is susceptible and 30% have got immunity. The next thing you're interested in is maybe spreading fast or slow, but how deadly is the disease? That is, how many people does it kill from those people that are infected? And that's called the case fatality rate, again, which has been on the media quite a bit. And so what you do is you take all the people who've ever caught the virus and you put that on the denominator, and on the numerator you put all the people who have died from the virus. So the number of people who have died from the virus divided by the number of people who've ever had the virus, and that gives you the case fatality rate. Two obvious problems there. We don't know how many people are really dying from the virus. And secondly, without mass testing, we don't know how many people have had the virus. The other thing is that if we're measuring the total number of people who have died up until today and the total number of people who've had the virus up until today, then we're not measuring really the total number of people who have died from those people infected, because those people who are infected today, they will die later on. So really we have to take the quotient of the number of people who have died as of today divided by the number of people who were infected up until, I think, either 7 or 14 days. So there's a whole lot of stuff around how you actually estimate the case fatality rate. And the third point where we might have a problem is, irrespective of how deadly the virus is or how fast it spreads, if it all comes in one little narrow window, it could overwhelm the NHS. And that means that other people who have other operations waiting, who need beds, will suffer. So those are three reasons why there is a problem. Out of interest, how did we find that equation for herd immunity? So herd immunity, we can do that by saying let a fraction k of the population be susceptible to infection. So they're neither currently infected nor recovered or immune nor vaccinated. And then we use the effective reproduction number, which is R0 times K, where 100 times K% of the population is susceptible. So to keep now RE less than or equal to 1, not R0, because R0 assumes that everybody in the population is susceptible, then we need K to be less than or equal to 1 over R0. So if we've got K less than or equal to 1 over R0, then we can say that 1 minus K will be immune. And that gives us the formula below. 100 into 1 minus 1 over R0 percentage must be immune in the population to ensure herd immunity. So if you plot case fatality rate against R0, and I took this slide from an American physician, Maria Conley, who I think adopted it from a graph by Isaac Florence. She forgot to add cholera as a bacterial infection. But you can see the 2019 Wuhan coronavirus. This was taken quite early on, so that's a rough estimate of what the Chinese estimated, I think, as the R0 number and the case fatality rate. If you look at all the other viruses close to this, then what you notice about them, they all have vaccines. And to the best of my knowledge, there hasn't been a vaccine for any of the viruses from the coronavirus family. One particular disease that's been eliminated is smallpox, which has been around for about 3,000 years at least. And it was removed by a process of intensive vaccination, of tracking and tracing and vaccinating in all remote parts of the world. And I think probably one of the reasons that was done was because smallpox is such a horrible disease, disfiguring and a very painful death. if you look at the numbers who die, who get these diseases every year and then die from it, you can see here that I've shown that seasonal flu is about 650,000 per annum who die from seasonal flu. If I was to add in Spanish flu, which of course doesn't repeat every year, it's between 50 and 100 million in total during the 1 to 2 years of that epidemic. So why is R naught so important? Well, it's used for modelling of transmissibility, severity of outbreaks and control, and it's usually modelled with ordinary differential equations. So if you've done any work in control or state space theory or anything like that, you'll be familiar with these simple types of equations. It's also often used as a threshold parameter, trying to keep it below 1, because this in theory will mean that the outbreak will become extinct. Although I don't know enough about this, but I believe some people say that it's not always an epidemic threshold parameter. So the problem with estimating R0, as with any parameters involved in this particular disease, that you only get an estimate and you have quite large confidence intervals. So how do you practically estimate R0? So you have an infected person A and a susceptible person B. You can break R0 down from a beta tau into this equation with 3 parameters. So T is the transmissibility, the probability that A and B will actually transmit the virus to B, and this parameter is the average rate of contact between A and B. So what's the chances that they're going to actually meet? And this is the duration of the infectiousness. So taking that into account, you can use extensive testing, contact tracing and modelling. You can estimate R0 in practice. R0 will change with time, and the London School of Hygiene and Tropical Medicine have produced these particular graphs. So if you go back to the origin of this particular virus and the outbreak of the disease, then you see the R0 number looks like this, and I've drawn the line for that important R0 equals 1. What's happened here is that, of course, the Chinese authorities have pretty much crushed that R0 number by a complete lockdown in Wuhan. So let's look what happened in the United Kingdom with R0, again from the London School of Hygiene and Tropical Medicine. So that's R0, including the period when China was locking down, and of course we were getting information coming in from other countries. And you might ask why that was. Well, I very rarely put pictures of politicians in my talks, but because this impinges directly on the information or the data that we're looking at, I have to say something about the Prime Minister. And over these dates, he was saying that he would hope to visit his mother on Mother's Day, that he was still shaking hands with coronavirus patients, and that he could turn the tide within 12 weeks and send coronavirus packing in this country. I suppose I get the impression that he wasn't really serious and didn't really understand what was happening, although the scientists did, and he was being warned by other countries. So R0, of course, has regional variations. The R0 value that I gave you on the previous page is the average R0 value for the whole of the country. You can see here that it looks like London has the lowest and northeastern Yorkshire has the highest. What's important, of course, is not just the R0 value, but it's the rate of change of the R0 value. London may be a positive differential going up, and northeastern Yorkshire may have a negative differential and going down. And I think that when you do the modelling, you model either small populations or you model individuals, and that's the difference between, say, the Oxford modelers and the Imperial modelers, as far as I know. Now, if we look at South Korea, it's got 52 million people. It's a real success story. It had one of the largest outbreaks in any city outside of China, but they really cracked down heavily, and 0 local infections, 250 deaths by the 30th of April 2020. That's across the whole country. There was no lockdown, but there was a very high-tech track and trace and isolate by what's considered to be the world's most connected country. Another important thing was that a lot of techniques that were used for, I suppose, surveillance, credit card tracing, mobile phone location logs, surveillance cameras, and a sort of Confucian acceptance of authority. These were repurposed for COVID-19, including protective screens at restaurants and drive-through clinics. So it simply shows, without making any political point, that you can reduce the virus spread by using technology. Now, Hong Kong is another success story. It's got 7.5 million people, about the size of London, but it's one of the most densely populated cities in the world, and yet it had just 4 deaths by the 16th of May 2020. And this was without any total lockdown. It also had extreme border closures from the very beginning. It had test, track, and isolate, and 99% of people in Hong Kong wore face masks from the outbreak of the virus. And for the 19th of March 2020, all arriving passengers by air were put on 2-week quarantine. They were also made to wear a wristband and had a tracker app which could monitor their movement around their house, because they weren't supposed to be leaving their house. So that certainly is incredible. 4 deaths by 16th of May 2020. So how many tests have we been doing in the UK? So these are the figures up to the 1st of May, when the government set a new target of 100,000. And what the chief medical officer said when asked about having test and trace at the very beginning, he said, wasn't likely to add a huge amount given the resources that we had. I put in brackets my own words, because what he failed to say, I suppose, is that, yes, of course, test and trace would have been very useful at the beginning, but what he was saying is that we weren't able to do it because we hadn't got the resources. And that, of course, is a political issue. In terms of the science, other countries that have done that have been incredibly successful. So let's look at countries that have implemented complete or partial border closures to foreigners. And this data is from the 15th of April 2020. So if you look here as a map of the world, those in red have got complete closure. Those in orange, I suppose, have got partial closure. And those in grey aren't doing anything really. And this is the UK, which is in grey. Now, the UK is going to introduce not complete border closure, but a 14-day quarantine for air passengers from the start of June 2020. And it's currently one of the few countries that has no checks or quarantine for air travel. Now, you might say this is a case of closing the stable door after the horse is bolted, but I couldn't possibly comment. So why do we need a reliable test? Well, you turn up at your doctor's, you have a test, you get a positive result, and then you track and trace all your contacts and you isolate them so the disease doesn't spread. If you get a negative result, then you can go back to work. Let's say you're a key worker, don't want to keep you at home if you think that you might be infectious, if we can prove that you're not. And of course, all that could be integrated with any new technology like the COVID app that comes out. Another reason for testing is we want to estimate what is the true or not number is. To do that, we need to test. We need to know the true numbers of people infected to work out the case fatality rate and how we manage to ease lockdown. So every aspect of dealing with this virus, I think, is predicated on having reliable and mass testing. So what is the problem with testing? I'm not talking about lack of resources or political will to do the testing. I'm talking about what are the actual scientific problems with doing a test. So you go along to see your doctor, you have a virus test, and you are told you either have a positive result or a negative result. And what you want to know is that if you're given a positive result, how certain can you be that you have the virus? Is it 100% certain? Or if you have a negative result, can you be 100% certain that you are virus free? So these are the important things, and this is what we're going to look at later on in this video. Now, there's an old saying that lies, damn lies, and statistics, but statistics never lie. When I say statistics never lie, I mean correct statistics. So if I say the average of 6 plus 4 is 5, that's a correct statistic. When I say lying with statistics, I don't mean saying the average of 6 plus 4 is 3. That's just an incorrect statistic. But you can have a correct statistic and you can mislead people. So take this. I've just devised a new test for COVID-19. Did it very quickly just last night, 5 seconds. And I've tested it in the whole of the UK population, and it was correct nearly 100% of the time. So the question is, am I telling the truth? If I press release that now, I'm sure I would have every radio station, television station on my doorstep. So yes, I'm telling the truth, but my new test is actually useless, because my new test is simply telling everyone who presents that they don't have the virus. And as the virus has a prevalence of 0.0021 or 0.21%, then my new test is correct 99.79% of the time. So if I said I had a test that was accurate with 99.79% accuracy, you'd think that was incredible. But in fact, this is just a paradox. So can we test for COVID-19 from the symptoms? So if we look at the symptoms, these symptoms, and compare that with COVID-19 and flu, we can see in both occasions it might be difficult to distinguish just from the symptoms whether you had common flu or whether you had COVID-19. There is, of course, the introduction of loss in smell and taste. So for various reasons, we do need something more than just looking at the actual symptoms. We need some sort of genetic test. So the two main types of tests. There are tests that test for the virus itself, and there are tests that look to see if you've had the antibodies to tell if you've had the virus before. And looking for the virus, there's two ways. There's a very famous PCR that everybody knows about now, that's been around, of course, not just for this virus, but for other things. It's called polymerase chain reaction, and it actually looks for the virus RNA from the swab. And the other test is an antigen test, and the test that looks for antibodies is called the antibody test. The PCR test takes from 13 minutes, that is if you happen to be standing in the laboratory with a technician, to 2 days if it has to be taken from, I don't know, doctor's surgery. You've got to take the swab, then send it off to the labs and get it returned. So what about the people who are asymptomatic? That is, people who have the virus but don't show any symptoms and feel totally healthy. Some work from Oxford University said that as many as between 5 and 80% of people testing positive could be asymptomatic. So all those people could be spreading and nobody knows about it. And of course, then if you're doing symptom-based screening, then all these will be missed. And the only way to learn the true extent of course, how many people are asymptomatic is when you have population-based antibody testing is undertaken. So dogs have also been trained to sniff asymptomatic carriers of the virus, just like they've been used before for things like cancer. Okay, we have to remember throughout that words matter in maths and statistics. When you say something in English, it's not as precise as an equation. So let me give you 3 examples. All the following 3 statements, they refer to false negative test results. A false negative test result is where you test negative, but you actually do have the virus, or you're infected. So let's take the first case. You walk in for a virus, check. What's the probability that you walk out and you've tested negative and you also have the virus? So there's 4 things that can happen. You can have a true positive, a false positive, a true negative, or a false negative. So what this is saying is, you go for a test, what's the probability that you have a false negative experience? Number B says you go for a virus test. What is the probability, given that you already have the virus, that you will test negative? And as we'll see later, that's 1 minus the sensitivity. So what we're saying there is, what's the probability, given that you already have the virus, that you experience a false negative? And lastly, this is the posterior probability. This is after the test. What is the probability, if you test negative, that you really do have the virus? And of course, that's the most important question. It's people who test negative, they want to know, do I have the virus? So put another way, what is the probability if I test negative that I will experience a false negative? So these are three different ways of experiencing false negatives. And depending on how you phrase it, and you've got to be very careful with how you phrase it, you get three different equations. There'll be more of that later on. Okay, so that's the end of part one. We've covered section one. We'll now go to part two, where we'll cover sections 2 and 3. We'll introduce the very basic maths associated with binary classification of a virus. Do you have it or do you not have it? And what is the probability associated with each outcome?